So in this section, we're going to start talking about derivative formulas. So we're going to learn some shortcuts that will allow us to take derivatives much more quickly than with the limit definition. Yay! Right. But it's important to point out that deriving these shortcuts, coming up with these shortcuts, all require the limit definition. So the time we spent doing derivatives the long way was important from the standpoint of the rigor behind learning the shortcuts. Also, each time we want to take a derivative of a new function, like a trig function or a log function, each time we're going to learn a new shortcut, we're going to have to go back to the limit definition in order to find the shortcut. So none of these shortcuts are possible without first going through the sometimes painful and tedious limit definition. So my first derivative rule is that the derivative of a constant is 0. Right? Because if you have a constant function, sketch a little constant function here at some height c. If you draw a tangent line anywhere along that line, what's its slope? 0. So the derivative function is y equals 0. So what is d dx of -7? 0. Derivative of a constant is always 0. All right, and then we have the power rule. These are going to be pleasant videos to listen to later. So the power rule says if you have n, any real number, x is your variable. If you want to take d dx of x to the n, you bring the power down, you bring the n down in front of the x, and then you copy the x, and then you subtract 1 from the exponent. So you have n x to the n minus 1. So what would d dx of x to the 6th be? 6x to the 5th. Bring the 6 down in front, copy the x, reduce the power by 1. How about x to the -4? -4x to the -5. Yeah. Yep, so bring the -4 down in front, copy the x, reduce -4 by 1, and you get -5. All right, how about d dx of the square root of x? Yeah, so it's helpful to rewrite the square root of x as x to the 1/2 first. So we're taking d dx of x to the 1/2, and then you can apply the power rule. So we have 1/2 x, we bring the 1/2 down. 1/2 minus 1 is -1/2. And if I wanted to be fancy, I could write this as 1 over 2 square roots of x. Excuse me. Okay. If c is a constant, and you want to take the derivative of some constant times a function, you can just bring the constant out in front, right? So you just differentiate c times the derivative of the function. So for example, if I want to take d dx of c times x, that's just c times d dx of x, right? I brought the c out in front of the d dx. But then what's the derivative of x? 1. So you can think of that in two ways. We could think of taking d dx of x as if you draw the line y equals x, the tangent line everywhere is going to have a slope of 1. Or you can think of using the power rule, right? We bring the 1 down in front and copy the x, and then when you reduce the exponent by 1, you end up with an x to the 0, and x to the 0 would be 1. So you can think of it either way. You'll get 1. So the rule in general is that constant multiples come outside the derivative, end up getting multiplied. So a couple of examples. If I want to take -2x to the 5th, my -2 coefficient just comes along for the ride. It's just going to be -2, and then take the derivative of x to the 5th, which would be 5x to the fourth. And then you could multiply those and get negative 10x to the fourth. Many people would do that in one step and think when you bring the 5 down, multiply by the negative 2 all in one step. How about d dx of negative 24x? What do you get? Negative 24. Negative 24x is a line. Y equals negative 24x is a line that has slope negative 24 everywhere. So that would be its derivative, negative 24. All right, so for any constant c, I want to find the derivative of c over x. So I want to find d dx of c over x. How could I rewrite c over x so that I could apply the power rule to it? C times x to the negative 1. Good. Just a rule of negative exponents. Okay. And then when I take the derivative, now I can apply the power rule. I take the negative 1 and I bring it down and multiply it by the c. So I get negative c x, reduce the exponent by 1, and I get to the negative 2, which would simplify to negative c over x squared. So no matter what number you have on top of that fraction, c over x, your derivative is going to be negative c over x squared. So what would d dx of 3 over x be? Negative 3 over x squared. We can follow that rule. Or we could start from scratch and rewrite that as 3x to the negative 1 and apply the power rule. How about negative 5 over t? d dt of negative 5 over t. What would my derivative be? 5 over t squared. Great. All right, we have some sum and difference rules. If you want to take the derivative of a sum of two functions, nice and handy rule, you can take the derivative of each function separately and then add them. Same with a difference. The rule is not so simple for products and quotients, and we'll do those another day. So number 11 here, I want to find the derivative of this polynomial. So I'm going to apply the power rule, the constant multiple rule, and the sum difference rule all at once to take this derivative. So because each of these terms is separated by addition or subtraction, I can take the derivative of each term separately. So what would my derivative of negative 5x to the fourth be? Negative 20x cubed. You bring the 4 down and multiply it by the negative 5, so you get negative 20x cubed. Reduce the exponent by 1. And then I can take the derivative of 7x squared, and I would get 14x. The derivative of negative 3x, negative 3. And then what's the derivative of 10? 0. Derivative of a constant is always 0. So this is my derivative. All right, so in your groups, I want you to find the first and second derivatives of f, and then we'll come back together to find the equation of the tangent line at t equals 2. Sorry, at x equals 2. All right, f prime of x to the fifth plus x cubed plus x is f. If I want to take the derivative, I'm going to apply the power rule to each term. So I'm going to get 5x to the fourth, take my exponent, put it in front, reduce the exponent by 1, and then the derivative of x cubed would be 3x squared, and the derivative of x would be 1. And then to find f double prime, I'm just going to apply the power rule again to f prime. So I take my exponent of 4, bring it down. 4 times 5 is 20. Copy the x, reduce the exponent by 1, plus 6x, and then the derivative of 1 is 0. All right, and then we want to find the equation of the tangent line of f at x equals 2. So I gave you a problem like this on your test, and we didn't do any in class examples like this before the test, and usually I'll put like one question on a test that's like a little different from anything we've done, but that you know enough to do, and many of you figured it out, so it was good. So if I want to find the equation of the tangent line, so equation of a line, right? You see, ignore the word tangent, that's just an adjective. That's just the kind of line, right? Equation of a line, what's the answer going to look like? Y equals mx plus b. This is what I'm looking for. Looking for the equation of a line. It happens to be the line tangent to f at x equals 2. How can I find the slope of the line that's tangent to f at x equals 2? It's the derivative, right? The derivative is the slope of the tangent line. I made you all say it with me, right? So the derivative is the slope of the tangent line. So m, my slope that I'm going to put into this equation, is going to be f prime of 2, the slope of the tangent line at 2. And then b, we'll figure that out later. Let's figure out what m is. So fm is f prime of 2. So I'm just going to plug a 2 into my f prime function. 2 to the 4th would be 16 times 5 is 80, plus 2 squared is 4 times 3 is 12, 92, 93. So 93 is my slope. So I'll go ahead and put that in. Y equals 93x plus b. All right, how do I find the y-intercept? I could plug in 2 for x, because I know if I knew a point that was on this line, I could plug in the x-coordinate and the y-coordinate and solve for b. So I need a point on my line. Point on that tangent line. Okay. Well, I know of one point that's on the tangent line, the point of tangency, the place where the line touches f. I can find the coordinates of that point. How do I do it? Yeah, put 2 into the f equation. Yeah. So I would have 2 comma f of 2. Right? That's a point on my line because that is the point of tangency. It's on the graph of f. It's also on the line. Okay, so this is going to be 2 comma, I plug a 2 in here. 2 to the 5th is 32 plus 8 is 40 plus 2 is 42. So 242 is on the line. So I can plug in 2 for x and 42 for y. And now I have an equation with only one unknown, b, and I can solve for the y-intercept. So what's 93 times 2? That's 186. Minus 42 would be 144. Did I do that right? Yeah, negative, right? Thank you. So that's my y-intercept. So then my final answer, the equation of a line, is going to be y equals 93x minus 144. So a new kind of question that just puts together stuff that you know about derivatives and stuff that you know about lines, you know, from a long time ago. Okay, so for 13, take a minute to find y of 2, y prime of 2, y double prime of 2, and y triple prime of 2. All right, so to evaluate y prime and y double prime and y triple prime at 2, I need formulas for y prime and y double prime and y triple prime. So I'll do those first. Y prime will be 3x squared minus 1. Just use the power rule on each term separately. And then y double prime, that would be 6x, and then the derivative of the minus 1 is 0. And then y triple prime is what? 6. Good. So y of 2, I would plug into my original y function. 2 cubed minus 2 would be 6. Y prime of 2, plug in 2 into y prime. 2 squared is 4, times 3 is 12, minus 1 is 11. Y double prime of 2, 6 times 2 is 12. And y triple prime of 2, no matter what I plug in, is going to be 6. That make sense? Okay, so I'm going to show you how to use your calculator to get these numbers, the 6, 11, 12, and 6. Just to confirm, not that this was that difficult, but it's nice to have sort of a backup confirmation to your own calculations. All right, so in the calculator, I'm going to go to y equals, clear anything that's there. And I'm going to scroll all the way to the bottom to y0. That's going to be my original y function. And the only reason I'm putting it there is because then y1 will be y prime, y2 will be y double prime, and y3 will be y triple prime. And then the number of primes will match the subscript on the y. So I have x cubed minus x. That's my y. And then I'm going to go up to y1, which is going to be my y prime. And instead of typing in the formula that I could get in my head, I'm going to type in nderiv, which is in the math menu. Oops. Math 8. And I want to put y0, which is where my function, my original function y is. So you go to the vars, y vars, function, and y0 is all the way at the bottom, comma x, comma x. And if you have a slightly fancier calculator, something will come up that looks like, when you press nderiv, you'll get d blank of blank evaluated at blank, right? So in here, you're going to put the x. In here, you're going to put the y0. And in here, you put the other x. So when I first showed you how to use your calculator's nderiv, this notation made no sense because we hadn't ever talked about Leibniz notation. So this should make a little more sense now. This is just d dx, which is what the derivative, what you're taking the derivative of, what x you're evaluating it at. And for now, we're doing at all x's. All right, so then in y2, that's going to be y double prime. So I'm going to take the derivative of y prime. So I'm going to do nderiv of y1. So I'm going to do math 8, vars, y vars, function y1, comma x, comma x. And then y3 is y triple prime. So I'm going to take the derivative of y double prime. So I'm going to take the derivative of y2, math 8, comma x, comma x. And then I'm going to quit and go to the main menu. And I'm going to have the calculator evaluate each of those functions at 2. So I use vars, y vars, function y0 at 2. So your calculator knows function notation, so you can just call up y0, put 2 in parentheses, and that knows to plug a 2 in. So we get 6, which is what we got here. And then for y1, I'm going to call up y1, y vars, function y1, plug in a 2, and I get 11.000001. Sometimes your calculator does that because it's finding the derivative numerically, which is like a numerical algorithm where it's like it's doing f of 2 plus h minus f of 2 all over h and just using a tiny, tiny h. All right, and then I want to do y double prime of 12. So I use y2, sorry, not 12, 2. I get 12. And let's see, vars, y vars, function y3 at 2. And illegal nest, I've taken too many derivatives of derivatives. It won't do triple primes. Just a limitation on my calculator. So this is part of the reason, we have to actually know calculus, right? This thing, this 11.000001, we have to know that that's really 11, and your calculator is just doing something funny. And it won't take the triple prime for us. So if we need that, we have to know how to do it. You can also do it all right in the home screen. If I wanted to find f prime of 2, I could type nderiv of x cubed minus x. That's my original f. Oops. And then comma x, that would be my d dx. I'm taking d dx. And evaluate it at 2. And I get the 11. Also have one more method. I can graph x cubed minus x. So let's go to y equals and clear out my derivatives. So I'm just graphing my y0, my original f, x cubed minus x. I'll do like a zoom 6. So if I go to the calc menu and choose dy dx, it's asking me for an x value, right? So I just type in 2, and it gives me dy dx is 11. This last technique only works if the point you're interested in viewing is in your viewing window, though. You have to be able to see 2 and the point on the graph, f of 2. Okay, so some work for you to start in your groups. We are practicing finding derivatives with the power rule and finding equations of tangent lines. So for each function, I want you to find a formula for its derivative, a formula for the second derivative, an equation for the line tangent to the graph at the specified point or x value, and then check, graph your original function, graph your tangent line equation, and make sure that it actually is tangent to the graph at the point they asked you for.